All right, let's go ahead and start talking about scientific notation here. So the purpose of scientific notation is to write really big numbers or really small numbers in a faster way, right? So for this one here, instead of writing out 41,000, 41000, all right, 4.1 times 10 to the fourth. Now this number really didn't save me any time to write in scientific notation. I wrote about the same. The reason that we're covering it right now is there is a number that we use in chemistry quite often that we'll talk about a little bit later on, where when you write it out fully, it's 602 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0 0. That's assuming I counted correctly here. But if I did, we should have 0, 2, and then 21 more zeros. Was I right? All right, I thought I might have. All right. So writing this out sucks. So instead in science, we often write out something like this, 6.02 times 10 to the 23rd. So this one, you save quite a bit of time by writing it using scientific notation, right? So we need to learn this skill even though we aren't going to use it all the time, okay? Yeah. What? To the 23rd power, is that what you mean? Yeah, so the reason this works is like every time I multiply by 10, the decimal place just moves over. So if I multiply by 10 23 times, it moves over 23 times, which gets me the number of zeros that I need. Does that make sense? Okay. Other questions?
Ryan, you get that. Otherwise, you're doing like 6 times 6, which is 36 times 6. Like that's what you're doing if you just put the 23 there without the 10. Do you get that?
All right. So now let's look at the parts of scientific notation. So we have the coefficient. The coefficient is the number out front. All right. Then you have times, and then 10 is technically called a base. In theory, you could have other bases, but in our world, you're never going to use a different base here. And then you have an exponent here. And the exponent is just how many times you're moving that decimal place. All right. Now, some key things to know. That exponent there can be either positive or negative. If I have a positive exponent, that means I have a large number, something bigger than 1. If I have a negative exponent, it means I have a small number, something smaller than 1. All right? Questions so far? All right. So now let's go into one way that we can convert between these. So converting from scientific notation back to standard notation. Here are some examples. All right? I take my original number, and then since my exponent is 3, that means I'm moving my decimal place by 3 places. So moving it 1, 2, 3 places. And when I do that, you'll notice that there's like an empty little spot here, right? If my decimal place is there, I need to fill in that empty spot with a 0. So my final number is just 2,130. So this 2,130 is the same as 2.13 times 10 to the third power. Questions? All right. Now, for the next one, it's the same idea, right? 7.5 times 10 to the negative 4. The only difference is here we have a negative sign. So because it's a negative exponent, instead of making my number bigger when I move my decimal point, I make it smaller when I move my decimal point. So if I move it to the left here, 1, 2, 3, 4 places, and I just fill in the empty spots with zeros, my answer then is 0.00075 when I convert. All right, questions so far? All right. Now, with these two numbers at the bottom, you can kind of understand why we start using scientific notation, right? Writing out 99.8 million, that's what that number is. Sorry, it took me a second. It takes a while with all the zeros, right? Or writing out 0.00000000567 takes a while. So instead of doing that, we write it in scientific notation. Okay? So now I want you all to try and practice. So see if you can do it. I want you to convert these 4 numbers from scientific notation into standard notation. Try it out. For the first one, it just says 1.7 times 10 to the negative 3. Now, it's important to realize that it has a negative here, right? Because it has a negative, that means our number should be smaller, right? So then I move my decimal place over 3 places, 1, 2, 3. And then my answer would be 0.0017. Right? My decimal is just 3 places over from where it was. For the next one, we need to move it over 4 places, but this one's the opposite, right? It should be a big number. It should be moving to the side that makes it larger, not smaller. So move it 1, 2, 3, 4 places, and then fill in zeros. Then my number is 67000. Question so far? All right. For 4.2 times 10 to the negative 1, we just need to move it 1 place to make our number smaller. So the answer is just 0.42. And then for the last one, we have to move it 0 places. So if we move the decimal place 0 places, it's just 7.4. All right, question so far? All right. Now, I said this earlier, but again, in reality, you'd probably almost never see this number written in scientific notation just because it's not necessary. This number would never be written in scientific notation. It's completely not necessary. And these two might be written in scientific notation, right? You're saving some amount of time by doing it this way, okay? Questions so far? All good? All right. So now on to our next operation we can do. For these, instead of going from scientific to standard, we're going from standard to scientific. So for each of these, we're just trying to figure out how many places we need to move our decimal so there's just one number in front of the decimal. All right? And then if we moved it to make our number smaller, that means, or sorry, if we started with a large number, that means that we're going to have a positive exponent. If we started with a really small number, then we have a negative exponent. All right? So for example, here we had to move our decimal place from behind the 4 over here 1, 2, 3, 4 places. So since we had to move it 4 places, then we would have 5.2314 times 10 to the 4th. Questions here? All right. Now notice when I did that problem, was there a decimal place written after the 4? No. But I still knew it was there, right? If there's ever not a decimal place, it's just after the last number, right? Because it's after the ones place. So you just assume it's there. You can draw it in if you want and then show where it moves. Make sense? All right. So once you move it, you then just write the coefficient times 10 to however many places you moved it. Okay? All right. Now let's try these. So we have 0.002, 567,000, 4, and 0.1234. All right, go ahead, try these out. See if you can do it. Let's go ahead and review our answers for these 4. So how can we convert from standard to scientific? In the first one, we're trying to move our decimal place so that we just have one number in front of it. When I do that, the number that I end up with is just 2. All right? So then I have 2, I write times 10, and then I move my decimal place 3 places. So my exponent is either going to be 3 or negative 3. To decide whether it's 3 or negative 3, I just need to think, did I start with a really small number or a really big one? I started with a really small number, so then I have 2 times 10 to the negative 3. If it was a really big number, it'd be positive 3. Okay? All right, so next, 567,000. We move our decimal place from where it starts. Remember, that's after the 1s if it's not being shown, all the way across until I just have one number in front. Then I just have 5.67, and again, times 10. And I've moved my decimal place 1, 2, 3, 4, 5 places. So because I moved it 5 places, it's going to be 5 or negative 5. But in this case, I started with a really big number. So it's going to be positive 5. Questions here? All right. Now, you'd never really be asked to write 4 in scientific notation. It's kind of useless, right? But if you did want to do it, we don't have to move the decimal place at all. So it's just 4 times 10 to the 0, because we didn't move the decimal place. And then for the next one, 0.1234, we just have to move the decimal place one place. So it's 1.234 times 10 to the negative 1. Okay? Questions here? All good? All right. So next thing that we're going to be discussing is how we take measurements in chemistry and how we can convert from one measurement to another measurement. Okay? Now, the math that we're going to be discussing is not new math. I would argue that a lot of you can actually already do this math in your head without trying. For some reason, as soon as we take it from like real world context that y'all are used to a chemistry context, y'all forget it. The goal of what we're going to be doing right now is to teach you the math and how we do it in chemistry using concepts you're familiar with, so that when we then take it to chemistry, it's easier to do. Does that make sense? All right. So when you take measurements in chemistry, there are 2 ways that you can do it if you just want to know how much stuff there is. The first is just count the number of stuff. Now, we have done this where we counted the number of stuff during class. Can anyone think of a lab where we had to count the number of things, and our measurement was just a number of things? Any ideas? Pennies, right? We counted pennies. Any other ideas of things that we counted during class? Properties of liquids lab, anyone remember? The number of drops that fit on your penny, right? So we counted a number of drops, not a mass of drops or a volume of drops, right? It was just a number, right? Now, the other way we can measure stuff is just with mass, right? I take it, I put it on a scale, it tells me how much, right? This is also similar to how you shop at a grocery store, right? You buy 1 loaf of bread, or you can buy 10 pounds of potatoes, right? You don't count the number of potatoes, you count the pounds. But when you buy bread, you count the number, right? It's just different ways to measure things, all right? Questions so far? All right. Now, you can also convert between these things, all right? So when you do that, you have something called a conversion factor. So you just take 2 equivalent things, you make it into a fraction that helps you convert. So for example, if I knew that 12 apples weigh 2 kilograms, and I want to buy 6 apples, instead of actually counting out 6 apples, I can just weigh out 1 kilogram, put it in a bag, and then go check out, right? If I know the conversion, I can then figure out the equivalence, right? And so what we can do is we can take an equals, like 1 dozen apples equals 2 kilograms. And we can turn it into a fraction like this. 1 dozen apples over 2 kilograms. Now, why do we do this? We'll talk about in a second. But right now, it's just important to know that we can. So I'm just going to do this first example where we write out conversion factors. And then y'all are going to try the second. So in this case, if we wanted to convert between inches and centimeters, I have this equivalence. 1 inch is equal to 2.54 centimeters. If I wanted to turn this into a conversion factor, into a fraction, I can write it in 2 ways. I can write that 1 inch over 2.54 centimeters, or I can write it as 2.54 centimeters over 1 inch. Now, the reason we can do it either way, where I can write it as inches over centimeters or centimeters over inches, 1 inch equals 2.54 centimeters, right? So it doesn't matter. They're equal. What's anything divided by itself? It's just 1, right? So I did something divided by it, something it's equal to, or something divided by something it's equal to. So both of these are just like 1, right? They're equivalent to each other. We're just writing it in different units, okay? Questions so far? All right, now it's your turn. Go ahead and try the next one. So write the 2 conversion factors for this equivalence. 30 milliliters equals 1 ounce. Go ahead and try it out. All right, let's go ahead and review this one. So most of y'all, as I was walking around, had this already. Let's just review it to be sure. So we should have 1 ounce over 30 milliliters, Or we can have 30 milliliters over 1 ounce. Either one is okay here. All right, questions? Yeah? So we'd be missing units there, right? So remember in chemistry, numbers are equally as important as units, which is why when we do our math, we write units. When we write our answer, we write units because we care about both just as much, all right? We don't want to leave off either one, all right? Questions? All good? All right, so now let's go into the actual math that we need to do here. So the process is called dimensional analysis. Now, the actual definition of dimensional analysis is a problem-solving method that uses conversion factors to determine equivalent values. Now, the basic math that you're going to be doing is going to look like this every single time. You take whatever value you're given in the problem, and you're trying to convert it to some other unit. All right? Now, when you do this, you write the given value, you multiply by some conversion factor that has the unit you want to end with on top, the unit you want to cancel out, or the given unit on the bottom, so that you end up with the desired unit. Now, to understand why this works, let's go back to some math review first. I think this is math that we can all do. Let's start with the easiest one. What is 5 divided by 5? 1. Right? 5 divided by 5 is 1. Now let's make it a little bit harder. What is x divided by x? 1. Right? So anything divided by itself. If I do 5 divided by 5, it's 1. If I do 7 divided by 7, it's 1. If I do x divided by x, it's 1. And if I do y divided by y, it's 1. Right? Doesn't matter what I divide. If I divide it by itself, it's 1. So now let's take it to a chemistry concept. What is grams divided by grams? 1. Y'all are learning. If you take anything and divide it by itself, it's 1. So now let's look at the original example of why I'm saying this. If I do given unit divided by given unit, what is it? 1, right? So if I do given unit divided by given unit, it's 1. So then I have 1 times desired unit, and that's just desired unit here, right? Now, this is getting abstract, right? It was easier for y'all when it was 5 divided by 5, right? But we're getting into less real stuff, which can sometimes be difficult, but it's still the same, right? If I do something divided by something, it can disappear. We cancel it out because it's just 1. Does that make sense? All right. So now let's do an example together. Now, if you read this problem before even doing any math, you probably know the answer. If you have 2 dozen apples, how many actual physical apples do you have? Someone say the answer before we do math. 24. Right? Now, the reason we're doing it this way is because I know that y'all know the answer. We just need to learn how to show our work and do the math when it's easy, so that when we get to chemistry and it's harder, it's a little bit easier to figure out. Okay? So starting off, just like we said before, I'm going to take whatever I'm given first. So in the problem, it tells me I have 2 dozen. So that's what I'm given. Now, every time you do a problem where you're converting from one unit to another, you're going to end up writing a dot, a line, and an equal. So if you hear me tell you, when you ask, like, oh, how do you do this problem? I say, do a dot line equal. What I'm saying is do a unit conversion. Now, let's go back to math class. What does a dot mean in math class? Multiply. What does a line mean in math class? Divide. So we're going to be multiplying something and dividing something to then get our answer. Right? So now we just need to have our conversion factors, right? Now, we're given an equivalence. We're actually given 2 of them. But in this problem, we're being asked to convert from dozens to apples. So the equivalence I need is the one that has dozens and apples. If I was trying to convert between dozens and kilograms, then I would need the equivalence for dozens and kilograms. but I don't need that one. Now, the first thing I'm going to do is just write out both conversion factors. I'm not going to need both, but I just want to have both in front of me. So my equivalences, or my conversion factors, would be 1 dozen over 12 apples, or I could have 12 apples over 1 dozen. All right? Now, I need to figure out how to select here. I need to pick the conversion factor that's going to cancel out units of dozen and leave me with units of apples. So if we're looking at this example up here again, I want to have the given unit on the bottom and the desired unit on the top. So if we look here, which one has the given unit on the bottom and the desired unit on the top? The one on the right or the one on the left? What do y'all think? Which one has the desired unit on top, given unit on bottom, right or left? Y'all are just guessing.
What's the given unit?
Let's check. So if we look up here, in the problem, we are given there are 2 dozen. We are asked to find the number of apples. So our given unit is dozen. Our desired unit is apples. Y'all see that so far? Okay. So then based on that, which one has our given unit on top? Sorry, given unit on bottom, desired unit on top. Left or right? Right. Do we understand now? Okay. So now I just need to fill in. So I have 12 apples on top, 1 dozen on bottom. Now let's talk about how I actually do my math. So the first thing I'm going to do is only do math with numbers. So if I look at numbers and ignore units, I have 2 times 12 divided by 1. So 2 times 12 divided by 1 is just 24. The same number that we came to when we just did this math in our heads, right? Now, the second thing I need to do is do math with units. If I do dozen times apples divided by dozens, something will cancel out. My dozen should disappear. So I'm just left with 2 times 12 apples divided by 1. So then my unit will end up being apples. Question so far? Yes? Nope. So if you want to, if it helps you remember, you could put over 1. Right? Because anything over 1, it's just the same thing, right? But there is no denominator to it. It's just 2 dozen, right? Now, if it helps you when you're doing your math, remember that this is technically a fraction and put it over 1, you're welcome to. Other questions? All right. So now I want to give you all a chance to try the next 2 on your own. So you're given 2 problems. These ones are about time, right? And again, time is something you're familiar with. You first asked how many minutes are there in 45 hours? And the second question, how many days are in 45 hours? All right, go ahead and try out both these problems. See if you can do it. So to start off here, the given number is 45 hours. And it's asking us to find the number of minutes, right? This 2-word set, how many, is a sign that it's about to ask you what they want it to convert to. So if it says how many minutes, or how many grams, or how many days, or however many things, right? It says how many, that's what you want to end with, all right? And then it will give you something else in the problem. In this case, it's 45 hours, right? So just like before, I write the number that's given in the problem, 45 hours. And then dot, line, equal. Okay? Question so far? All right. So now from here, I need to think about what I want to cancel and what I want to end with. Now remember, from what we did up here, whatever unit I'm given, is going to end up being on the bottom of my conversion factor. Whatever unit I want to end with is going to go on top of my conversion factor. So in this case, I'm trying to cancel out. I want to get rid of hours because that's what I was given. I'm trying to get to minutes because that's what I want to end with. So now that I have my units filled out in my conversion factor, I just need to figure out my numbers. So it tells me that 1 hour is 60 minutes. Now again, I think that's something that most of y'all could have figured out here, right? There's 60 minutes in an hour. So I just need to fill in my numbers now. There is 1 hour in 60 minutes. Okay? So now everything is filled out. I just need to do my math. So I'm going to do numbers first and ignore units. So I have 45 times 60 divided by 1. I go to my calculator. I type in 45 times 60 divided by 1. I end up getting 2,700. Now I need to look at units. For units, I have hours times minutes divided by hours. When I have that together, the hours will cancel out, right? I have hour divided by hour. So since hour is divided by hour, it disappears. So the only unit that's left is minutes. This make sense so far? All right. Now that we've done a second problem, I want y'all to try the third one on your own, see if you can get it done. All right, try it out. See if you can get this third one done. All right, let's go ahead and review this last problem here. So, for how many days are in 45 hours? All right, the given number is 45 hours, right? It's the number given in the problem. And since it says how many days, I know I'm trying to end in days. Okay, so I write the given, dot, line, equal. I'm trying to cancel out a number of hours. That's what's going to go on bottom. I'm trying to end with a number of days. That's what's going to go on top. Question so far? All right. Now let's fill in numbers. So I need to find the equivalence that has both days and hours. So here, day, hour. So I have 1 day equals 24 hours. I then fill in my numbers with their matching unit. So now I have 45 times 1 day. Sorry, 45 times 1 divided by 24. So if I plug that part into a calculator, I get 1.875. And now if I look at my units, I have hours times day divided by hour. So it's just hour divided by hour. That part cancels out. I'm just left with day. So I can cancel out hour and hour. I'm just left with days. Questions here?